Now, do you remember how to take the derivative when x and y are all mixed up? Because we can still do implicit differentiation even though a natural log is involved. Process is still the same. So we have d dx, because we're going to take the derivative of this expression with respect to x. And we're going to communicate that, right? Oh, not plus. I'm going to take the derivative of both sides. So when I take the derivative of x cubed, I get 3x squared. 2 ln of y gets a little interesting. So you have 2, and then the derivative of natural log of y, you remember that's supposed to be 1 over u, quote unquote, so that's y, times the derivative of y. Well, the derivative of y is dy dx. Remember, that's what we're solving for. The derivative of y cubed is 3y squared dy dx. You always take the derivative of the given variable, and the derivative of 4 is 0. So now you're an algebra student. You are trying to solve for dy dx. Because this is now a fraction, there is a little bit of level of complexity here. We're going to go ahead and move that 3x squared over. So I have 2 over y. I'll go and put the dy dx out. Make it a little simpler. 2 over y plus 3y squared is equal to negative 3x squared. Now at this stage, I would definitely get a common denominator here. I would not try to divide by this and then end up with a complex fraction there. I would go ahead and get my common denominator. That's what I would do. So I'm going to go ahead and multiply by y on the top and the bottom here. So I'm going to rewrite this completely. dy dx times 2 plus 3y cubed over y equals negative 3x squared. And now to solve for dy dx, all I need to do is multiply by the reciprocal. So now you get negative 3x squared y over 2 plus 3y cubed. So that is your derivative. Dy dx is all alone. You're going to be tempted to try to reduce things, but remember that addition sign kind of throws me off with that. So there's nothing that can be reduced, and there's nothing that can be factored out. So that is my final answer. Example 10 asks a slightly different question. It's got to prove that this equation is a solution to this differential. Remember, a differential equation is just a derivative equation. It's an equation that involves a derivative. That's all. But I actually have the second derivative and the first derivative here. Well, what does that even mean? But wait, I have y, so I can get y prime, and I can get y double prime. I have that information. So the question is, if when I plug those back in here, do I get 0? So let's find y prime. The derivative of ln of x is 1 over x. And obviously the derivative of 4 is just 0. So you've got 3 over x. Now if you want to treat that as 3x to the negative 1, that'll help a little bit when you go to find the second derivative. So second derivative is negative 3x to the negative 2. So if I plug these back in, do I end up with 0? Now there's also an x there, so don't forget. So you've got y double prime, right? But you're supposed to be multiplying that times an x plus 3 over x. Does that equal 0 is the question. Is that a true statement? That's what we're trying to prove. So these do reduce. So you get negative 3 over x plus 3 over x. Does that equal 0? Yes. Right, so because that is a true statement, 0 equals 0, we can definitely say that y equals 3 ln of x plus 4 is a solution to this differential equation. Remember, a solution is just the original function, and the differential equation is just any equation that involves a derivative.